everyone, Katrina here, and today I'm going to teach you about double angle identities. Be sure to subscribe for more videos like these. Okay, so let's dive in. In my previous videos, I've covered compound angle identities and equivalent trigonometric expressions. Double angle identities is just another identity that you can add to your long list of identities and tools for solving trigonometric equations as well as conducting trigonometric proofs. So be sure to watch to the end to see how we can derive these double angle identities, which really help us simplify problems. You might often consider or run into problems where you have like sine 2 theta or cos 2 theta, and you're wondering, how can I go about and solve these? From my previous videos, I've taught you how you can solve trigonometric equations when you have sine theta, cos theta, tan theta, but what happens when you have this 2 in front of your theta, when you have essentially this double angle? So I'm going to show you really cool identities that you can use to simplify these problems, and I'm also going to show you how to derive them so that you have a deeper understanding of what they are. Okay, so we're going to start with the first one. Let's start with sine 2 theta. So we have here, like I said, sine 2 theta. And what is the identity for this? Well, let's rewrite this as sine theta plus theta. And does this look familiar? If you understand compound angle identities, you can see that essentially we have sum A plus B. We have two angles within the brackets of our main angle. So essentially what we can do here is we can apply the rule or the compound angle identity to solve for this. So if I do that, my problem now becomes sine theta cos theta plus sine theta cos theta by the double angle or by the compound angle identity. And what happens when I simplify this? Well, I have two terms that are the same, so that means I can just have a coefficient of 2. So now I simply have 2 sine theta cos theta. And there you have it. We've already derived the first one using compound angle identities. So sine 2 theta equals to 2 cos theta sine theta, and now we simply just have single angles for both of these. So that is great. Sine is a bit, I find, easier than cos because there's only one double angle identity here, where cos actually has 3 different identities. So let's go through and derive all of them. So we have cos 2 theta. We're going to do something similar such that we have cos theta plus theta. And again, this is like our angle A plus our angle B, and we're going to rely on the compound angle identity here. So that means we have cos theta minus sine theta by our compound angle identity. Well, we can rewrite this then as cos squared theta minus sine squared theta. And there you go. That is identity number 1 for cos 2 theta. So let's put a nice little yellow box around that. But let's challenge ourselves to take this further and derive 2 more. So as an intermediary here, I'm going to remind us of Pythagoras' identity. And this is derived from Pythagoras' theorem, and this tells us that cos squared theta plus sine squared theta equals to 1. This is the identity. So we can rewrite this in the following way. We can say then that cos squared theta equals to 1 minus sine squared theta. Okay, so what if we were now take this and then substitute it in to our cos squared theta over there? As a result, we end up with cos 2 theta equals to 1 minus sine squared theta and then minus sine squared theta. And we can go ahead and then simplify this problem. And after we simplify it, what do we get? We get 1 minus sine squared theta minus sine squared theta, which equals to 1 minus 2 sine squared theta. And that is our second double identity for cosine. So I think at this point we can guess what the third one's going to be. Looking at our Pythagorean's identity, we isolated for cos squared theta. But what if we isolate for sine squared theta? We see then that sine squared theta equals to 1 minus cos squared theta. And what we're going to do there is, we'll zoom out there, we're going to replace or sub in this 1 minus cos squared theta into our sine squared theta over here. So as a result, what do we get? We have that cos 2 theta equals to cos squared theta minus, again we're subbing this in for sine squared theta, so minus 1 minus cos squared theta. Let's expand out our negative to both of these terms, which means that we have cos squared theta minus 1 plus cos squared theta. So we can take the cos squareds and add them together. So as a result, we have 2 cos squared theta minus 1. And that is equal to cos 2 theta. And this here is our third identity that we can use if we have a double angle in cosine. So again, these double angle identities are great because they simplify your double angle into a single angle, and you already have the necessary tools using your unit circle and other identities to help solve the problem and potentially find exact solutions if you can leverage your special triangles. Also, make sure to remember these when you're doing trig proofs, and definitely stay tuned. I'm going to be making some videos on trig proofs coming up soon, and these videos will show you how you can use all of your identities and knowledge of trig and put it all together to solve these really neat looking proofs. And with that, I will see you next time. Please subscribe for more videos and drop a like if you enjoyed this one.